Just to give a little bit of idea that how Professor Aditi and Ujjwal Sen with their groups, they work there. They are a 24/7 researcher. So they will have they have a large group there. Already Aditi, as you can see, that she's almost, very young. Already she has her students settled all over India and outside as faculties and postdocs. So they have a large group, and all of them, they even travel together. They go to various places, and even research goes on there also. So I have seen Aditi and Ujjwal walking with their students and talking about physics, mathematics. So Professor Aditi Sen was the winner of Booty Foundation Award in 2012, and of course this prestigious Bhatnagar Award in 2018. And let me tell you that she's made history by, she's the first female physicist to get this coveted prize. And she works in quantum computation, quantum information, quantum this optics, and quantum cryptography, and many body physics. And she's a prolific researcher. With her group, if you see, just find out, she's one of the most, most prolific researcher in India and abroad. Professor Aditi Sen there.
Thank you, Kolanda, for such a nice introduction. And yeah, I mean, I must say that it's really nice when I get the invitation from Kolanda. Although Kolanda told that I work this 24/7, this is also true for Kolanda, because I also get inspired, because we used to almost sit together in the pantry in two different places where the students, postdocs are always around Kolanda, and they are doing research together. So in many cases, he helped me a lot when I joined initially at HRI, almost now 11, 12 years back. So that was really nice. Now Kolanda has moved. That's also a bit sad, but also good that we have a new connection, new place. And okay, so maybe I come to what I am going to talk. So as it is in the name, so I will be talking about technologies. And the technologies that I am going to talk is about quantum technologies. That means the technologies that we are planning to build is based on quantum physics or quantum mechanics. So we are quite aware of several technologies, and in this pandemic situation, the two technologies probably that we have used most are computer and communication devices. So I think these two play a key role during last 10 months and so, and which help us to communicate each other, to have this kind of conference and so on. So it would have not been possible if we don't have these two devices. So I think in this audience, it's not required to emphasize the role of these two technologies in our life. The communication devices can be broadly classified into two categories. One is without security. What do I mean by without security is that you send any messages and that doesn't require any kind of lock and key system. And so, for example, now I am talking. I mean, I'm sure that many people are listening who are in this in that seminar room. At the same time, there are other people who can also listen. I mean, there is no harm on that. On the other hand, there are some communication devices which are called secure communication or the cryptography, just now Kolanda mentioned. So that communication require key as well as lock. So suppose there are two parties who wants to send some message from one place to another. So their aim is to send the message in such a way that no other person can get that message. I will explain in a bit more detail on that. So our aim is to create, or is to build these two technologies, or these three, what I have talked, based on quantum physics or quantum mechanics. So that I am going to convince that they, in next 45 minutes or so, that if I build technologies based on quantum mechanics, they will be more efficient than the one that we are using now. So let's start with something, why we should build quantum computer. Because a computer that nowadays we use, for example, the desktop laptop, and we are happy with it, and we know that they're very good, they're very efficient, and they serve most of our purposes. So not only this desktop laptop, but there can be a workstations where so many computers are connected, and they are more powerful, or they can perform more powerful task than the normal desktop. And so these computers serve our purposes, and these are useful in many fields, like educational field, hospitals, banking, government offices, and probably again in this COVID situations, even the students are every day now, now using computer to get their lessons. So they are useful, and we use these computers to write documents, to use internet, but at the same time we also use these computers to do certain mathematical problems to solve. So this is important because that what we are going to discuss. Before I go to discuss about some problems, mathematical problems that we can solve in a classical computer, or the normal computer that we are using, let's discuss that what are the units that are essentials in classical computers. So classical computer, the basic unit is bit, which is one of the 0 or 1. Now, typically, we give some input to the computer, and that is translated into bits, which are strings of zeros and one. Then there is a manipulations of these numbers by using some logic gates, and that we know there are some universal logic gates for a computer. And finally, we get another strings of bit, which is the output after the manipulation. And this output can be translated in any languages. So zeros and one can be translated in, for example, in English, or in any language that we wish to learn. So let's come to the first problem that I'm going to solve in a classical computer. So suppose I give you a number, and you have to tell me whether the number is prime or not. Okay, this, if it is a if it we talk about the prime number up to 100, then even the school children can understand what are the prime numbers. And if I go to 1000, it will be difficult. But suppose I give you a number which is a 10-digit number. Now you have to tell me whether the number is prime or not. Now this number, actually, which I typed randomly, only keeping in mind that the last number is odd, last digit is odd, then I actually find out that this number is not prime. It is divisible by 7. So my idea, or our idea, is to find or design a program which can solve any n-digit number. So here I have given 10-digit number. So you can write a program in your computer which can tell you at the end of the day whether the number is prime or not. Now, if this 10-digit number is a 100-digit number, you can understand that you have to write an efficient program. So suppose I give you an n-digit number, an arbitrary digit number, and you want to design a program which can tell you that whether a number is prime or not. Now, at the same time, you want to write a program in such a way that it can give you the answer in a reasonable time. That means, of course, if it takes, say, 1,000 years, then it is not useful. So we want, that actually mathematically called polynomial time. So although this problem looks so simple, but it was unsolved till 2002, when three people from IIT Kanpur have solved this problem, and they propose an algorithm which they which actually tells us that if we give you a number, then it is sorry, something. Yeah, so if I give you a number, then it is prime or composite, and it will give this answer within a polynomial time. So polynomial means if I have an n digit number, it will be n square, square root of n, and so on. So this is a good news. So these are the three people. Actually, it's an old picture of them, around 2002, I think this is the picture. So this problem is solved, so it's a good news. Now I go to a second problem. So this is called a prime factorization problem. It's again related to prime numbers, but now I will give you an integer, and you have to tell me whether a number is integer is has whether this or how many prime factors that integer has. So for example, if I give you 45, you know the prime factors as 5 to 3s. If I have 72, you can find out. And again, the trick is same. So I will give you a 8-digit number, and then you have to find out. Of course, you can do it. I mean, even a school child probably will be able to do it, this 8-digit number, and you can find out these are the prime factors. So the point is again that I give you a 8-digit number. If I give you a 80-digit number, whether you can write a program which can solve it efficiently. Not only I write a program, because I can be stupid, but anybody in the world wants to write a program which can solve this problem in an efficient way. Now, till date, the data tells us the following, that if I have a, say, around 120-digit number, then if there are some kind of 1600 powerful workstations working, then in principle, it may take 8 months to give the answer. So the efficient algorithm which are available till date, which can solve this prime factorization problem in a classical computer, uh, approximately can take this months time if it is around 120, and if you double it, right, 250 digit, then it takes also almost the age of the universe. So this tells us, I mean, this is kind of bad news. So if I talk more mathematically, then to factor an n-digit number, any available algorithm in our computer. Now here, our computer means not the computer that I am using, for example, this laptop for giving a talk, or the desktop that you are using, but any powerful computer in the world, okay, what we can think of, takes almost exponentially n steps. That means if you increase number of digits, so if you increase n 120 to 125, it will be the step size required are exponentially increasing. This exponential n is a bit cheating, because more mathematically it will take this number, people know that, and this I think is called mathematically sub-exponential. So these number of steps are required to solve this problem till date, whatever algorithm is known to us. So there is no efficient classical algorithm till date, and so that's a bad news. But the good news is that if you use quantum mechanics, then one can show that this problem can be solved in an efficient way, and it can be solved in a polynomial time. And this was done by Peter Shor in 1994, known as Peter Shor's algorithm. And as I said, that better efficiency means solving in polynomial time. This is Peter Shor, a US mathematician. Now, after this discovery, or around this time, there are several algorithms proposed where it was shown that the quantum mechanics help to reduce steps. So if, say, to solve certain problems, classical computer requires n steps, it was shown that to do this task, quantum computer, or the computer that are built on the best on the principles of quantum mechanics, can take less number of steps, like square root of n or so on. Okay, so just a very brief very brief means really very brief. What is quantum mechanics? As we know, that quantum physics describes microscopic particles, which are atomic or subatomic levels, and it was formulated around 1920s by several great physicists: Einstein, Schrödinger, Heisenberg, Dirac, uh, Shottendranath Bose, and many others. And here, of course, these etal are important because there are many important scientists whose name I haven't mentioned, including all experimentalists that actually helped to shape the quantum physics. So this is probably you have seen in many places. This is a Solvay conference in 1927 in Brussels, where there are almost most of the physicists who help to shape the quantum physics, which we learn now in colleges and universities. This was done. Importantly, there is a woman, Marie Curie. So if you notice, okay, so in quantum physics, what we do that if we want to describe certain situation in a physical system that correspond to vectors in a linear space with an angle defined, and a linear space in which an angle is defined is known as Hilbert space. Probably this is not required here for the introduction. Now, if we talk about a two-dimensional complex Hilbert space, so field is here complex numbers, then these two-dimensional complex Hilbert space can represent spin of an electron, for example. Now, as you have seen that in a classical computer, the basic unit is bit, which is say from between zeros and one, as I have described. Now we have to define a basic unit for quantum computer. And this is known as qubit or quantum bit. So this QU for quantum and this is bit. What is qubit? Qubit is a two-dimensional quantum state. So which you can think can be represented like that. And these are the eigenvector of sigma z, for example, which I denoted as up spin, and this is down spin. If I consider spin degrees of freedom, you can consider different degrees of freedom, and this alpha beta are the complex number. So if I look at the kind of this can be represented in a pictorially or geometrically in a sphere. So for example, if the poles denote the up or down spin, okay, then they are orthogonal. Then the surface of the sphere, all the points in the surface of the sphere actually is represented in by this phi vector. So this surface of the spheres, all the points represent qubit. So this is the basic unit. And this up spin and down spin, if I, instead of spin degrees of freedom, if I consider different degrees of freedom, so it can be left rotations, right rotation, as etc. Then this can be represented usually by 0 and 1, exactly like in a classical bit where you have 0, 1, 1. But it has some more property, as I will show you. So in particular, there is something called superposition principle in quantum physics, which tells us that in classical world, we get a cat which is alive, or we get a cat which is dead. But quantum physics tells us that there can exist quantum states which can be alive plus dead. So we can have a state like 0 and 1, which are orthogonal. But quantum physics tells us that there can be a state which is alpha 0 plus beta 1. And this is not for different alpha beta value. You can take the inner product and can show that they are not orthogonal. So this is actually crux of this Shor's algorithm. So quantum mechanics, in particular superposition principle, ensures the power of solving this factorization problem that I have discussed. So, just like in classical computer, there are universal gates like AND or NOT or NAND gate. Similarly, in quantum computer, we also have universal gates. So, for example, there are gates which are known as Hadamard gate, which is defined on a single qubit, like 0 and 1. And 0, you go to a superposition, 1, you go to another superposition. These two are again orthogonal, and you see that this is actually the power of quantum physics, which is not possible in a classical world. And there can be a gate, universal gate, which is a 2 qubit gate, where it is defined on two states, 2 qubits, which is in a tensor product Hilbert space. Now, the question is whether it's just a theoretical prediction. It's not. This is experimentally achievable. So this is a quantum technology timeline. You can find it in, which was published from European Union. And they said that they are about to get, they are planning to get quantum computer around 2035. But there are several small scale quantum computer has already been built, and several technological giants like Google, IBM, Microsoft, Intel, there are other new companies, startup companies, they also have started to build a quantum computer. In particular, you can find even in Google that there are IBM 20 qubit chip computer, and up to now, I think, to my knowledge, it's Google 72 qubit chip is the maximum number of qubit that computer has been built. So it is a computer with 72 qubit, and you can find out several websites where this kind of information is available, is every day updating, because I think just a few days back there is a quantum supremacy experiment where they show that the quantum computer can perform something which is not yet which is not possible by a classical computer from China. So there are a lot of advancement every day going. So here I just want to mention that this is actually a technological revolution that one has to understand. For example, if I make a better and better lantern or candle, these candle or lanterns technology is not same as the bulb or LED bulb that we use. So this is a technological revolution because it's a completely different technology. Similarly, making better and better classical computer doesn't lead to a quantum computer. The efficiency that we can get in a classical computer, we will not be able to get in a quantum computer. It will be much faster, much efficient. And so we may think that, okay, because if we, even in my time, when I was in the university in 2000 around there, that time, the computer was, it was like a huge, it was extremely slow. And now everybody has a computer, even a small, this iPad where we can do many efficient things. So we can think that, okay, if we wait more years, then we will be able to build computer which can be as efficient as quantum computer. It's not, because it's a different technology, because the classical computer is based on classical mechanics, classical electrodynamics, classical information theory. On the other hand, quantum mechanical or quantum computer will be built on quantum physics. So it's a revolution in technology. Okay, so now in the next part, I will talk about the communication devices. So there are two types, as I said. So again, it is not, probably this audience do not need any emphasis of the usefulness of the uh, communication devices. And we also see already a kind of revolution in quantum devices with the electronics revolution. So you see that I am from this area of the Brown, where we used to write letter, and we used to post to get to know the informations from our relatives and friends. And now, even my daughter cannot think to write later, because she also thinks that we have to send SMS or WhatsApp or email. So this is a completely different mindset that already I also have. Now, so we know that the revolution in communication devices are extremely important and very useful in our daily life. So any communication devices involve at least two parties, Alice and Bob. They are situated in two distant places that we are talking about. And Alice is the sender, suppose, and Bob is the receiver. It can be Alia, Borun, it can be two people, powerful people, and not the common people. And here the aim is that Alice wants to send some information from her place to Bob. Now, in this talk, I mean, we will be talking about the informations which can be classical as well as quantum. Now, classical means that Alice wants to send some bit to Bob, and or Alice want to send some quantum state to Bob, and this can be a qubit. So actually, one can show that if you use quantum physics, then sending classical as well as quantum information, uh, uh, you can get some advantage. I will highlight mainly the quantum part because of the lack of time. So I will be showing that if you want to transfer qubit, then you get if you use quantum mechanics, it will give better efficiency. So this is quantum state transfer known as quantum teleportation, and this was discovered in 1993 by 6 scientists. And as I said, Alice's task is to send an arbitrary quantum state to Bob. Now, as I told you already, that this arbitrary quantum state means the surface of a point in the surface of the sphere. Now, in the surface of the sphere, there are infinite number of points. So to encode this infinite number of points, Alice actually requires infinite amount of classical communication. That means infinite amount of bits. Now let's see whether quantum device can give you some advantage or not. So the task is the following, that Alice has some input state which is in a quantum state, and Alice wants to send this input to Bob. Of course, Alice can put it in a box. I mean, box means a box, a sophisticated box, which is where the quantum state can be kept, and send it to Bob. But this is not allowed. This physical transfer is not allowed. So how she can do? Okay, so the proposal was the following, that if Alice and Bob prepare a bridge between them. Now, this bridge is a quantum mechanical bridge. That means Alice and Bob prepare a quantum mechanical state between them. And then if Alice performs some quantum mechanical measurements and sends her measurement results to Bob via just a normal phone call that we use, and this phone call actually requires 2 bits of classical communication, then finally Bob can get the state that Alice wants to send. So by using quantum device, if Alice and Bob a priori prepare a bridge between them, that is a shared quantum state, then this protocol tells us that 2 bits of classical communication is enough to send an arbitrary qubit from Alice to Bob. So you see, here we get a 2 bits of classical communication. In a classical device, we need infinite amount of classical communication. So we actually can have an infinite resource reduction by using a quantum device. So this is a quantum teleportations, probably you have heard of because it has been published in several science fiction journal, newspaper, etc. These are the 6 scientists who have done this, proposed this thing. Again, I mean, the way I have presented looks like a magic, like Alice and Bob is preparing some kind of bridge, and it's kind of magic, but of course not, because the ingredient is quantum mechanics, or ingredient is the properties of the bridge that Alice and Bob has made. And this bridge is known as entanglement. And if you are interested to know, then there is a nice review article by these 4 scientists from Poland, actually whom I did my PhD, with them also. My supervisor is someone different, but I work very closely with them. And they have a very nice review article. And if you're interested, you can look at that. So there are also articles reviewing. We have written some chapters, and there is a recent review article that we have written on that the properties of the bridge, where we discuss. Now let's define what is the property of the bridge that I'm talking. So that's Alice and Bob. They are in two different labs. And suppose the complex number X is with Alice, which I marked as pink. And then the black ones, these are another complex number, and they are with Bob. As you see that if I have this expression, the first line, then the second line can be written like that. So it's a X and X plus Y. So it's kind of, you can factorize, right? And this is exactly called the unentangled state. So quantum mechanically, if Alice prepares some quantum state in her lab, Bob prepared a quantum state in his lab, then the joint state is in the tensor product Hilbert space, and this looks like that. And these states are called the unentangled states and useless states, because if the state shared between Alice and Bob, that means the bridge is prepared in this state, then they will not be able to perform the teleportation that I have just described. So if I have a spin degrees of freedom, Alice prepares up spin, Bob's prepare up spin in his lab, then they are mathematically look like that. And this is useless or unentangled state. So useless or unentangled states are those states that Alice and Bob can prepare even when they are situated in two distant locations, like in Kerala and Allahabad. To prepare entangled state, Alice and Bob has to come together. So it is impossible to prepare an entangled state when they are far apart location. Then you can tell, okay, how they will prepare the bridge. You can think that there is a source which produces an entangled state. Source can be situated, say for example, in Delhi. They prepare this entangled state, send one particle to Calicut, another particle to Allahabad, so that at the end of the day, Alice and Bob share an entangled state between Calicut and Allahabad. Now, mathematically, how it looks like, again, the pinks are with Alice and black are with Bob. Now, the state cannot be factorized, as you see, because these are all complex numbers, and this is, I mean, real or complex, you cannot factorize. So the simple algebra, when applied to certain vectors, lead to non-factorizable vectors are called the entangled state. These are mathematically. So in Hilbert space, or in the state terms, if a joint state in the tensor product Hilbert space cannot be written like phi A tensor product phi B, then they are called the entangled state. And this is the property of bridge that we require to prepare or to perform the teleportation task. And if you look spin degrees of freedom, this state probably you have seen even in your graduate class is called the singlet state. And here again, I use spin degrees of freedom. This state you can show that cannot be written in terms of this phi A tensor product phi B. And so these states are the entangled state. This is the property of the bridge that we require to perform teleportations with a maximum efficiency. The way I have presented looks like things are very nice and simple, but it is not. The definitions are well known. So we know how to define entangled state, how to define useful or useless states. But given a quantum state, it is not easy to find out or to detect whether a state is entangled or not. So in particular, if an experimentalist give me a state and tell me whether, can you calculate and tell me whether a state is entangled or not, it's not easy to find. Until that, there are certain criteria which one can use, but still we don't know any universal criteria for arbitrary quantum state. Now, probably with the teleportation success, people now want to build a communication network where everybody is connected via quantum channel. So that's probably the dream. And actually, in that directions, we work in at HRI. So we want to share entanglement over large distance. That's a main challenge nowadays. So, for example, recently we have shown that if you have a one-dimensional quantum network, for example, this one, as illustrated in the picture, and if I want to share entanglement between, say, 1, 2, 3, 4, how to share? We actually gave a proposal in this recent work in physical review research. This can be go on. We can, instead of 1D, we can have a two-dimensional quantum network, which also we have. So the aim is to share quantum resource or this entangled state in pre-decided nodes. And we gave a proposal how to do that. So it's towards building quantum internet or quantum communication network. In over the years, we have worked extensively on this topic. Again, the question is whether it is only theory. It is not, because there are a lot of experimental achievements. So for example, if you talk about photons, then the photons have many degrees of freedom. So one of the degrees of freedom is polarization, which is a right-handed and left-handed circular polarizations can represent qubit. And it was shown in 2017 that in a Chinese group led by Professor Pan, they used satellite to share an entangled state between two cities, which are 1,200 kilometers away. So this is up to now, this is the highest distance in where the entangled state can be shared. So just to give you an example, that in 2020, it is a reality that, for example, Kolkata Guwahati, which is around 1,000 kilometers, one can share entangled states. There are several other physical systems like ion trap, where the ions are trapped in a, say, for example, in kind of harmonic oscillator, the ions are trapped. And this is called harmonic trap, where you trap the ions, and these ions internal levels can serve as a qubit. And recently it was proposed that by calcium ion, not proposed, they experimentally actually demonstrated that they can entangle 20 such qubits. There are several like superconducting qubits, and there are many other physical systems where the entangled states can be built. This teleportation and computation experiments can be done, like ultra-cold atoms, superconductors, NMR. So finding physical systems where quantum computers can be built and finding physical system where quantum communication can be realized are important question in this field, in this quantum computation and quantum information theory field. In other words, finding useful systems like entangled states. Finding a physically realizable systems where entangled states can be found is also another important question, because entangled states, as I have shown you, are resource for performing quantum teleportation. And this is the work that we are doing at HRI in this direction. So our aim is to find a physical system. So mainly it's a many-body system. It's an interface of condensed matter physics and quantum information. So we work extensively with our students. Okay, so I think I have some more time which I can spend for the cryptography. So I will talk about quantum secure communication. So here the aim is to send classical information securely. So again, there is Alice and Bob. Alice wants to send some classical information, that means bit, to Bob. But there is an eavesdropper in between them. That means, suppose Alice wants to send some information to Bob. Alice has to send in such a way that the third party or eavesdropper cannot gather information about what she is sending to Bob. Now, eavesdropper, on the other hand, eavesdropper aim is to gather as much information as possible from the flowing information that Alice is sending to Bob. So Alice's aim is to encode the information in such a way that when she will be sending that information to Bob, eavesdropper will not be able to get the information. So this is another layer of layer that we required in a communication task. And we know that these are very useful. For example, in internet banking, of course, always we get this message from bank that don't share your password to anyone. So, for example, your date of birth don't share, and so on, so on. So, this is because this password can be shared. So, the way is that we want to communicate our bank authority in such a way that no third person can gather that information, so that our bank account can be cleaned by this eavesdropper, right? So that's the aim. So this is internet banking. It's same for when we do internet shopping nowadays. But as you can see, this is also related to national security, because if there is a war, then the two opponents are there, and the their aim will be not to send their strategy, or not to know the strategy by the other opponent. So from ancient time, this is important. So there is Julius Caesar's time already, there is a cryptography system. World War II, which you have probably learned that there are different cryptographic system has been used. And so uh, we are aware that there are a lot of security. I mean, we do very successfully internet banking, online shopping. So we have a very secure classical cryptographic system. So classical cryptography system is very strong. But this classical cryptography system security is based on the belief that some mathematical problems cannot be solved in classical computer in polynomial time. This is extremely important. So, for example, the classical cryptography that we use is based on the fact that the prime factors of an integer, which I have discussed in the beginning of my talk, cannot be solved in a classical computer in polynomial time. That's important, right? So suppose I encode in such a way that based on this prime factorization problem, then we know that eavesdropper cannot solve it, because eavesdropper requires few months or even a few years to solve it. So that means actually, but I have already told you that this mathematical problem, the prime factorization problem, can be solved by using quantum mechanics. That means if eavesdropper has a quantum computer, then eavesdropper can break all the secure cryptography system that we are using. So quantum mechanics makes all current crypto systems insecure. So what to do? Again, the remedy comes from quantum mechanics, because people have proposed quantum cryptography, whose security is based on the validity of quantum mechanics, which remains secure even when we have a quantum computer. And these are the two protocols which I'm not going to discuss, but this is proposed by Bennett Brassard and Eckert in 1991. So just to tell you the basic principle, to generate quantum key, Alice sends a sequence of randomly generated quantum state to a receiver instead of bits. Now, the important point is that if eavesdropper wants to gather information, then eavesdropper has to perform certain measurement on that quantum state that Alice is sending to Bob. Important point is, laws of quantum mechanics tells us that if eavesdropper wants to disturb the system, then Alice and Bob can understand that. And this is known as no cloning or no disturbing theorem. This is done by these two scientists, Hooters and Zurek. And this tells us that disturbing of quantum states can be detected by using quantum mechanics. This is Bennett, Brassard, and Arthur Eckert. And they propose this quantum key distribution, which nowadays are used for different purposes. Again, it's not only theory. So one of the first long distance experiment was done in Geneva in 2001. So it's between Geneva, this is a lake, and this from the Geneva city to Lausanne, they have performed this quantum cryptography. And importantly, I mean, this quantum cryptographic machine is quite a reality, because, for example, in Football World Cup in South Africa, there was a project called Quantum Stadium Project. So they use this Stadium project to secure the keys so that there is no baiting take place, and this is to prevent baiting. So this is between Durban's stadium and another joint operations center. So they use quantum cryptography. They use also in Geneva election. And nowadays, if you search in Google, you will find that you can even buy quantum crypto machine. But here I want to stress that quantum crypto machine is required when we have a quantum computer. And as I have already told you in the beginning, that quantum computer is reality only up to a small scale. So in some sense, if we do not have a quantum computer, the classical cryptographic system that we are using are perfect and they are secure. Once quantum computer is in the market, then all the crypto system like internet banking and other things, they all will be insecure, and we have to change our all crypto systems to quantum crypto. These are the 4 people who initially have this experiment in Geneva, led by Nicolas Gison. Now, we also work in this direction. So still the security of quantum crypto system are under research. So there are several questions has to be answered or understood. And we recently have proved some complementary relation. And there is also another important concepts which play an important role in the security of quantum cryptography is called monogamy of entanglement. So as it is in the picture, if 2 parties, say Alice and Bob, is entangled, then monogamy of entanglement tells us the third party cannot be entangled with Alice and Bob. Now, when Alice and Bob are having a maximal entanglement, the third party cannot be entangled. But if they have a non-maximally entangled state, then third party can be entangled. So monogamy of quantum relation deals with the trade-off between this correlations of these 3 parties or more. And we have written a chapter of a book on this, and we have done extensive research on this from around almost last 10 years or so. We also have proven recently something called no masking theorem, which actually has an implications on quantum cryptography involving many parties. I'm not going to discuss, just to give you a hint that lots of research going on in this direction. So I come to the end of my talk. So I think I am able to convince you that quantum mechanics can revolutionize computation and communication skills that we are using, and specifically in the communication skills with and as well as without security. So quantum cryptography is already a reality, as I have told you. So now we are heading towards quantum internet, which I have just give you a glance, that quantum communication network. Of course, there are many people working like us. And possibly after that, we are planning to reach quantum computer, a full-scale quantum computer of around 1,000 qubits or so. Here again, I want to tell you that if we are able to build a quantum computer of around 1,000 qubits, then only we can show that our quantum computer is more powerful than the one that we are using. So classical computer, or classically available, as powerful computer as possible. So we need time, and there are a lot of open questions because there is a lot of problems of decoherence, etc. And which has to, there are a lot of work going on how to keep quantum state for a long time. That is important to build quantum computer as well as quantum communication. And also the quantum memory. For example, if we want to keep a quantum state in a lock, then how long it can keep its quantumness. So the quantum property will be kept and can be used. So this kind of devices are under research. And there are a lot of other devices have been built over time. So this quantum technology is second generation quantum technology that we are talking. And this is, there are a lot of nice areas, nice directions. If you're interested, you can contact me. So this is the kind of current group of mine. So I have this 5 PhD student, and these 3 are also joined as a PhD at HRI and doing project with me. Shiladitya was a postdoc and group who extensively worked with me in last 2-3 years, and he now left to abroad. And this is the total QIC group at HRI. So we have around, currently I have 15 students, but almost 6-7 students are doing joined as a PhD at HRI, are doing projects with all of our faculty members. There are 5 postdocs and 3 faculty members. And so thank you very much for your attention.
Yes, thank you so much, Aditi. It was a wonderful exposition, and I know that time was limited, but really you could give us a very vivid picture of how the things are being going on. And now it's the time for you guys here. So Aditi, these are all our MSc PhD integrated students. They have just joined, finished the quarantine period, and they have just finished their BSc. So if you have any question for Aditi, yes.
Hello?
Yes, please.
Yeah, so I have 2 questions. So the first one is, so I have 2 questions. The first one is, you talked about quantum computers solving the prime factorization problem, right? So
Yes.
I'm wondering if quantum computers can also solve the other algorithm, like the Lyman algorithm. They can solve everything like that. Like in the standard public key cryptology, you have this thing called the public key generation algorithm, which is done on some hard platform groups so that the lock problem cannot be solved. So
That can be solved also.
that can also be solved.
This is actually a same people, Peter Shore and others also, they have solved that problem that you were talking.
So for any general platform group, you can solve.
And that's not yet known.
So
But
for,
the problem that you are talking about, this RSA and other things, that is solved. But the questions that you are asking, still we don't know. There are several open questions, of course. Slowly people are building, but the RSA code, this thing that is built on that lock problem that you said, I just talked about prime factorization because it's much easier to explain, and so but that can be solved. Yes.
yeah, but so in that sense, the quantum computers are not really a threat, right? If it's
No, I mean, up to now, whatever cryptographic systems that are, I mean, classical crypto systems that have been built based on all the algorithms, that can be solved. But in general, any classical algorithm, okay, so there are several boundaries of communication complexity, right? There are complexity classes of which can give you polynomial, not polynomial, and so on. So we still don't know all the boundaries. That is not.
the second question is, if you have quantum computers, is there no need for generating public key? Because it seems like you mentioned something called monogamy principle.
No, actually, I have done a bit cheating because, it's not a time, because I cannot explain everything. So the point is that, as I mentioned briefly, although I haven't said clearly, because quantum crypto system is not quantum crypto, it's a quantum key distribution. It actually tells us that Alice and Bob can share key even when they are far apart, they are located in far apart distance. After sharing the key, they just can use the one-time pad which a classical crypto system use to share the information. The point is that in one-time pad, as you know, that you have to share random keys, okay? But that these random keys should be random keys, same random keys that are available to Alice and Bob, and only Alice and Bob. These random keys are prepared by using quantum mechanics. And
Okay.
that's why quantum cryptography actually is not quantum cryptography, it's a quantum key distribution.
Okay. So
After that, you use one-time pad.
I asked this because you said something called the information that you transmit, you cannot perceive that without interfering with it. So I thought there is no need for public key probably
No,
because
no, no, no. You actually use the same trick like classical one, but the first thing, because as you know that the main loophole in the one-time pad is how to share these random keys, because that was the main problem that in the Second World War it was happened, because if you somehow have this key common to eavesdropper, then you are gone, because then eavesdropper will later on they can. And in classically, the sharing key is possible if Alice and Bob are together and then they go to far apart location. Okay. So there is always, even the machine which actually produce the key can be a cheater, because you have to think that eavesdropper actually put the machine which creating the key, right? So because you have to think that the eavesdropper is most powerful person in the world or even in the universe. So so the main trouble is this first sharing of key, and this sharing of key is done in case of by using quantum mechanics. And quantum mechanics ensures that even when Alice and Bob in two distant locations, they can share the key, because the reason is that Alice can prepare the key, sending the key through a quantum channel. And when they send, if eavesdropper wants to gather that information, then Alice and Bob will discard the entire protocol, because Alice and Bob will know. Of course, there will be a resource which will be, which will be using, because they have to discard the entire protocol. But okay, when we are talking about security, probably everybody puts a lot of resources.
but the recipe is same, right? They have private
Yeah.
keys, public. Okay.
Then there is a one-time part, and then this public and this private thing, and everything will be same. Yeah. Yeah, that, lack of time, I haven't discussed in that detail, because then only cryptography will take the entire time.
There's one more student.
Oh, I can see a known face, no? Yes. Yes, please.
Entangled state, why we are using complex number only? Means why if we take some real number, like we can factor,
Yeah, we can get.
we can
That's a more general. So if you know, in a Hilbert space there is a vector, and in a vector space as well, you have a vector as well as field, right? Field can be complex as well as real. So of course, if you can have a real number, you can also have an entangled state. Now the problem is that if you have that we can understand already from mathematical point of view. If you have a real space and if you have a complex space, that of course will give you a more. So there are actually a research going on where people try to see if we restrict the field to be a real. So if I consider, instead of the complex vector space, if I consider real vector space, what are the things that we will not be able to do? So there are questions, but still you can consider real vector space can do a lot of things. Actually, most of the time we simplify, because complex number is hard to, handle.
Yeah, Akhilesh has a question.
Yeah, please.
I am quite curious, like using satellite, we can exchange this entangled state. So, really, whether we can observe this entangled state,
Yes, because usually in satellite you prepare because satellite you can think of a source, okay, and then this from the satellite, photon is a light kind of, you can think what do you call light particle, or very naive way to tell. So satellite prepare a entangled state, then send one particle to say Calicut, another particle to Allahabad, okay. Now you have to tell between Allahabad and this Calicut, you have to show whether really the shared state is entangled or not. That one can show, that they have shown, because all these now long distance photonic experiments are done in a free space. They call free space. So actually from satellite to land is much more, there are less noise, because there is only a noise because of the environmental decoherence, only because of this, which is environment. On the other hand, there will be much more noise or decoherence when we do an experiment between Calicut and Calicut and Allahabad, because there will be a lot of pollution, etc., etc.
So how one ensure that the key is got the genuine person? Maybe because the signals coming from satellites, many people can access it. So how we ensure?
Yeah, no, that has to be done with different process. So including the classical error corrections and the privacy amplification protocol has to be done in a way, and then they can ensure that they have. So you have to, for example, part of the key has to be you just share in a say publishing in a newspaper, both of them, and then they can just see. But then they discard that part, and the rest they will keep, so that they are sure that whatever they have generated, it's not a single photon coming. You have thousands to make a key generations, or the key to be a big long string. In one time pad, as you know, the most important thing is that the strings of 0 and 1 will be as long as possible, so that you don't reuse it. That's a basic principle of one time. So that kind of things also has to be ensured in quantum scenario.
And I also heard like this quantum computer must be kept in a very low temperature. How much low one is to
that question is still under process. I mean now they can okay, they can go very low temperature nowadays, in, as you have heard, in quantum experiment. But I think these kind of questions, even with temperature, we have shown that, for example, in our HRI, there are a lot of work where we have shown that even with a high temperature, you can keep some kind of entangled states. Actually, sometimes entanglement can increase with temperature, and that may help to actually do some processing tasks. So these are under questions. This is still a kind of, I mean, not a general answer can be given at this point.
Yeah, so it seems like the seminar room, Aditi, is over. So we can move into Zoom. If there is any, if there are any participant through Zoom want to ask questions, can unmute themselves and ask Aditi. Yeah, it doesn't seem like. So I'll move it to Srijit. Srijit, is there any YouTube chat question?
No, sir, there are none here.
Okay, so that's great. So people are very convinced. So I just want to make one comment. I mean, not a thing. So just to assure people like Vishwanathan that we mathematicians are also trying. There is something called post-quantum crypto. So the PQC is coming in a big way. Like people are trying to use super singular elliptic curves. And in fact, they have shown that that is resistant to Shor's algorithm. If you change that crypto to that, the classical one, to super singular things, and there are lattice theory which people are working in. So mathematicians are also trying. If
I think that mathematicians are very efficiently doing classical crypto, which actually I really understand very little, but I know that the people are trying very hard, and there are a lot of work going on.
Yeah, just like the worry of Vishwanathan, that what will happen if the really crypto computer, whether everything will collapse and all. But I just want to assure both the physicists and the mathematicians are working together so that this information system is not going to collapse. So be sure of that. We have researchers like Professor Aditi Sen, they and others. So thank you so much, Aditi. It was a wonderful talk and we really enjoyed it. We are hoping that as soon as the situation normalizes, you are coming with your group. Okay. Thank you so much. Thank you. Take care. Bye-bye.
Bye.